Hi, good afternoon. Good afternoon.
Good afternoon.
Oh, good morning.
It is still morning.
I'm sorry. Okay. Well, let's continue our discussion of chapter 9, okay? Numerical integration, and today we will talk about 2D. Let's first review what we did last lecture. Numerical integration in 1D. So essentially, let's assume we already transfer everything into the natural coordinate. So the integration is from -1 to 1, and then function of theta, and then d theta. And the concept is very simple. Any integration can be written as a sum of some weight times the corresponding function, the integrand value at certain selected point. So let's say this is f at theta I, and then weight I. You add them together depending on how many integration points you use, just add to the total number of integration points. So integration, numerical integration is actually pretty simple conceptually and also in terms of implementation. If you think of differentiation and integration, they're kind of opposite of each other. When you do a closed form differentiation, you can always do it as long as you have the expression. But when you try to get a closed form integration, a lot of times you cannot obtain any closed form solution. But numerically, the easiness of the two cases just reverse. Numerical differentiation is a little bit more difficult than numerical integration. Because integration is something times something, add them together. Okay? Integration is, I believe, is a little bit more difficult than that, but still doable though. Right? So this is 1D. Now, if we extend the idea into 2D, let's say we have y1, y2, let me write dy here, and then x1, x2, and then dx. Then with a one times a function, or let me write it this way, f as a function of x and then y, and then dx. I write it this way because there will be no confusion which limit applies to which variable. Okay, this way, this x1, x2 applies to x, and the y1, y2 applies to y. And sometimes people write it this way: f x y dx dy. I am not sure what the professor said in calculus course. Will the first one correspond to this one or the other one? I usually understand it that the first integral sign is related to this, and the second is related to that. Okay? Because if you're not clear, then you apply the wrong limit. But if you write it this way, there's no confusion at all. Okay? So I will keep that way. And then we apply the same idea here. This time we use the natural coordinate well, we write x as a function of natural coordinate theta, y is a function of natural coordinate eta. Okay? Alright, correspondingly, the limit of y1 is changed to eta 1. This is eta 2. But because eta 1 and eta 2 are natural coordinate, the limit will be from -1 to 1. So this is the eta. And the limit of theta will be also from -1 to 1. And then here, the function is transformed to be a function of theta and eta, like this. Okay? So when you substitute x as a function of theta, y as a function of theta in here, of course, function f becomes a function of theta and eta. But then we also need to transform dx and dy. It turns out when you have two variables you integrate together, the dx dy represent a integration area element. The transform of an integration area element involves something called a Jacobian, okay? And this is d theta. What is the Jacobian? The Jacobian is the determinant of this expression. Partial x, partial theta, partial y, partial theta. Here partial x, partial eta, and then partial y, partial eta. This is a 2 by 2 Jacobian. Okay? So once you know the functional form of x, depending on theta, you can calculate that, and then similarly you can calculate the others, like that. So this is a 2D integration. This is in 2D. Once you express the integration in this form, now you can use the numerical integration. Okay. Use numerical. It becomes sum of the integrand. Now this time the integrand includes the function f as well as the Jacobian. Okay? The Jacobian itself could be a function of theta and eta. But a lot of times it turned out to be a constant. It depends on the functional dependence here, okay? Alright, so now we have f, and you select certain locations. Let's call these theta I, the integration point, and the eta I, and theta, again at these theta I, eta I location. So this is the integrand at a certain location, then times the weight. Because you integrate twice, the weight will be multiplied twice. Oh, this is j. Let me write it this way. Now you have I and j, okay, because you have two integrals, 2 dimensions. Theta will go from I and j, and eta can also go from eta I to eta j. So the summation with respect to 2 dimensions will be summed together. One is I from 1 to n, and then you also need to run j from 1 to n. Okay? And the weighting function, with respect to theta, you have one weight, wi. With respect to eta, you have another weight, wj. That's formula. So the integration of this numerically is written as this. Okay? It may be a little bit more straightforward if you look at. We represent it graphically. Okay? Here we have theta. Here we have eta. Let's talk about a 2 by 2 Gaussian integration. Then theta will take on 2 locations. Here is theta 1 and theta 2. Eta can also take on will also take on 2 locations, this one and this one. So the combined locations will be 4. Okay? This is theta 1, eta 1, theta 2, eta 1, theta 1, eta 2, theta 2, eta 2. Okay? So you need to pick 4 locations, calculate the functions at these 4 locations, which is here, and times the weight and add them together. So that's how to do a 2D numerical integration. So let me box expression here. Okay. All right, next, let's use an example to demonstrate it. Let's say we have an integral r, which is x squared plus xy squared, and then dx, and then dy. Okay. The limit for x is from 3 to 6. The limit for y is 1 to 3. Okay. So to avoid confusion, let me draw something like that, so you know which corresponds to which. Well, to do that, of course, this is a pretty simple polynomial integration. We can do it by hand. So let's do that. First, by hand, 1 to 3. You integrate that. X squared is 1/3 of x cubed. Okay? And then x is, when you integrate x, it gives you half x squared. And y squared is still there. And this one, put the limit of x from 3 to 6. So the first step, you finish the integration with respect to x. And put the limit in, and it turns out that is 1 to 3, and that x is 6 power 3 minus 3 power 3, and divided by 3, that gives us 63. And then you can also calculate that. Putting on in these two limits is 13.5 y squared, and then dy. Okay. And now you can integrate that again. The constant will be 63 times y. It becomes linear. This becomes 13.5 and 1/3 y cubed. Okay, and then the whole thing, the limit is 1 to 3. That's a very simple expression to evaluate. At the end is 243. Okay, let me box that. So this is the integration when we do it in closed form. What we are going to do next is to evaluate it again, but using the numerical formula. Okay. All right. Next is numerical integration. First, we need to transform the global coordinate to natural coordinate. The natural coordinate should run from -1 to 1. Okay? It's very easy to map these to a natural coordinate. It turns out that x, if you use this relationship, and again, use the formula, the midpoint of the two limits plus half the length of the limit of the interval times the natural coordinate. That's the formula. Similarly, y is equal to 2 plus eta. So if you do that, it will transform the integration limit, both of them, from -1 to 1. All right? The next, we need to calculate the Jacobian. The Jacobian, by definition, is the determinant of partial x and partial theta. Here is partial y, partial theta. Here is partial x, partial eta, partial y, partial eta. I put that in. This will be 1.5 here y is independent of theta, so this is 0, this is 0, this will be 1. So that's a very simple determinant to evaluate. Just this times that minus this times that. It's 1.5. Okay? Alright, now we can directly apply the numerical integration formula, which is this. Okay? Alright, the function is, well, let me write it out explicitly. Limit is from 1 to 1, negative 1 to also negative 1. Now this expression is transformed. X is equal to that. So we need to put that in 4.5 plus 1.5 theta, that is x length square. And then 4.5 plus 1.5 theta, then times y square, which is this guy, 2 plus eta square. Okay? And the Jacobian now is 1.5. 1.5. And then d theta d eta. Alright, once we have the expression, we just need to directly apply that. So the first point here, remember, we are going to use a 2x2 Gauss integration, okay? So the first one will be this function at theta 1, eta 1. So it's 4.5 plus 1.5 theta 1 square plus 4.5, 1.5 theta 1 square, 2 plus theta 1 square, and times the Jacobian 1.5, and then times the weight W1 and W1. Okay? This is the first term when I is 1, j is 1. And then when I is 2, we will have the second term, which is all this here. This is theta 2. This is theta 2. The rest is the same. Here is W2. Okay? The rest is the same. Like that. And then the third is when I is 1, j is 2, and this time we will have this. This is become theta 1. This is theta 1. This is eta 1. And W1. And theta is eta is become 2, okay? And then W2, like that. Okay? The last term will be theta, I is now 2, j is 2, so this becomes theta 2. This is theta 2, and eta is also 2. Let me see, check everything. 1, 1, 2, 1, 1, 2, 2, 2. That is correct. This is W2 and then W2. Okay? So what are these theta 1 and theta 2? Theta 1 is equal to eta 1 is equal to 1 over 1 root 3. Theta 2 is negative theta 1. Eta 2 is negative eta 2. Or let me write it this way. Negative 1 root 3. And also W1 is equal to W2 is equal to 1. I checked the tables in the textbook, okay? We derived it yesterday. And put all this in. This one turned out to be the first term. Here is 1 root 3, 1 over root 3, 1 over root 3. This is 1 over root 3, and this 1 and 1. And use your calculator. The first term is 96.65a. The second term here is negative 1 over root 3, same. And this one is positive 1 over root 3. Okay, put this in. You have 56.018. And the third term, this is positive 1 over root 3, same. This is negative 1 over root 3. Turn out to be 59.482. And then plus the last term here, negative 1 over root 3, negative 1 over root 3. This is also negative 1 over 3. And all these ways are just 2. Okay? Each is just 1. And this term turned out to be 30.841. Okay, the total 243, which is exactly the same as what we obtained using the closed form solution, as it should. Okay. Well, for this simple example, if we compare the numerical with the closed form is simpler because we integrate that. It's shorter, and this is longer when we write it. However, in terms of programming, this is easier to program because it doesn't matter what is the functional form. You write a function, you know the expression, you can always evaluate it. So at certain point, 4 points, doesn't matter for computer, 4 points, 40 points, you can do it very, very fast. And then you just times these, times the weight, and add them together. So it's very easy numerically, okay? But any functional form, unless it's polynomial or some other elementary functions, a lot of times you cannot integrate it in closed form. So that's why we need to use numerical integration in the FEM program, okay? And you're going to do that a lot later. Okay, this is a 2D numerical integration. Now, if we specialize it to the finite element formulas, the formulation will be very similar to that, but the function f will include those shape function or the b, the derivative of the shape function, which is the b matrix, etc. Okay, so let's now apply the numerical integration to the FEM problem. Okay, the element stiffness finite element equation or statement is as follows. We derived that in chapter A, I believe. Okay, is this in the weak form? You integrate it with respect from element 1 to the total number of elements B matrix transpose and D matrix and then B. Okay, again, this is over each element, and then dV times UA. This is like that. Okay, this is the total When you add them together, it gives us the global stiffness matrix. What inside here is a element stiffness matrix. So when you have the global stiffness matrix times the nodal displacement for the whole model, it should be equal to, and again summation, shape function, transpose, body force, dV integrated over each element, and again from 1 to number of element. This is the contribution of that body force. By the way, the body force here is also in a vector form, okay? Then, second, we have this contribution from the natural boundary condition or force boundary condition, which is shape function transpose times the t vector and then ds over each element, and E is from 1 to number of element. So this term is the contribution from the natural boundary condition. And then if we have non-zero essential boundary condition, there is also a contribution in the force vector form, but it comes negative. Remember, initially it's in the left-hand side, but because it's now we move it to the right-hand side, so it's minus negative. And then we have B transpose D matrix, D is the material matrix, and then B0. B0 is the B matrix related to the prescribed boundary node. Okay. Sum together, E is from 1 to number of element, and then dV. All these times U0. And U0 is the prescribed nodal displacement. This integration is over again as element. Okay. Now you can see we need to do a lot of integration. Here we have one integration, which is the element stiffness. Here we have another integration, we have another integration, and another integration. Okay? It turns out this one and this one, they are almost the same. So we're going to talk about how to integrate these in this lecture. Now the body force integration involve a little bit extra derivation. So we're going to talk about that next lecture. Okay? So we will talk about that and this, and then this is the next lecture, and then once after next lecture we are ready to program it. Well, at this point, it's almost almost ready for numerical integration, except that we need to transform everything into natural coordinate. Okay, because the Gaussian integration point is given in natural coordinate. The limit is from -1 to 1. Okay? So we need to do that. All right, how to do that? Well, we will use the natural coordinate. Let's assume remember, we use in 2D instead of using those midpoint plus half the length times theta kind of thing, we make use of the shape function. So this becomes n1 x or I, nj, xj, etc. Okay, depending on the number of nodes we use. This is the 4-noded element. We can also use 8-noded. It turns out the 4-noded element, the variation within the element, the displacement is linear, okay, or bilinear in this direction, in x direction and y direction also. For the 8-noded, as you can see, in one direction, through 3 points, you can fit a parabolic relationship. So it is quadratic this way and quadratic that way. So it's quadratic in both x and y. And these turn out to be a much better, a more accurate element, because when displacement is quadratic, the strength, which is the derivative of the displacement, will be linear, right? A linear function allows, when the strength is linear, stress is also linearly related to strength, so stress will also be linear. So it can change. Then that is more accurate. So instead of using that, we are going to use that. Because in this way, the stress will be constant. When you try to use constant elements to fit a varying stress field, you have a stepwise approximation of function. This one, you have a linear, a piecewise linear fit of a function, which is much better than a step function approximation, of course. Okay. All right. So anyway, we can write this as M matrix times the nodal coordinate like that. With y is similar. Okay. Now with this, we can then calculate Jacobian, because this natural coordinate is a function of, let me erase that, is a function of theta here, and then the nodal coordinate. This will be a function of eta, and again y of the nodal value. So with that, we can calculate this, right? Oh, this is x, partial theta, partial y, partial, this is eta, I'm sorry. Eta. Okay, so J is null. Therefore, this one B transpose D matrix and then B and then dV. So this is the focus, because that's the element stiffness, okay, will be transformed into, now this is in volume integration, so it is 3-dimension, 3D. But because the problem we are going to solve, or the program we are going to code, will be a 2D FEM program. The thickness is a constant, so it's uniform. Okay, so the third direction, the integration will be just, all these things are not a function of z, so they are constant as far as integration with the z dimension is concerned, and the plate or the body is also uniform in thickness, so we call it T. So that will finish the integration with respect to z direction. In x and y, because of this natural coordinate, the limit will be changed from always -1 to 1. It's -1 to 1. Okay. So now this B is a function of eta and theta, theta and eta, and this is transpose. D is material constant. It's not a function of coordinate. I'm running out of space here, so I will write it here. T, -1 and 1, -1 and 1. B, which is a function of potentially eta and also theta and eta, transpose. D, which is a material constant, stiffness matrix, okay, which is a constant. And then B, theta, and then eta. And don't forget that Jacobian. Dx, dy, we will have this Jacobian J here, right, which is this one. And then transform the integration element into d theta and d eta. So this first step will be to transform the integration from global coordinate into local natural coordinate, but it is still in integration form, okay? All right, once it's here, we know what to do, right? The example I went through just show how to integrate it with respect to theta and eta, 2D. And so the next step will be write it into a double summation. So in fact, each of these integral is changed to a summation. This is number of integration points. Let me just write n here. J is also from 1 to n. So B, theta I, eta j, transpose D matrix, and then B, theta and I, eta and j, then Jacobian, and then Wi, and then Wj. And in principle, the Jacobian may also be a function of theta and eta. So let's put theta I here, eta I, to indicate that dependency. Okay? And then don't forget the weight, which is Wi and Wj. All right, let me box that. This will be the expression you need to program your element stiffness matrix. Okay? We will use 2x2 Gaussian integration, okay? Because a quadratic variation 2x2 is enough. A 2x2 integration is actually good for up to a cubic functional form, okay? So it's more than sufficient. And this one will be handled almost exactly the same way, except that B will become B0, right? The rest is the same. And then the textbook also mentioned, if you like, you can also do a 3x3 integration. A 3x3 is no more difficult than this. What, in terms of program, you just change the n to 3. This is to 3. But of course, those theta I and Wi will change accordingly. Okay? Let me draw it graphically. A 2x2 integration looks like this. This is the element. When you transform coordinate into natural coordinate, every element is just a square of size 2, 2 by 2. Okay, this is from -1 to 1. This is -1 to 1. So a 2-point Gaussian integration, the integration point is somewhere here, and here, and then here, and here. It is biased a little bit towards the edge because it's 0.577 something. Okay, so it's something like that. This is 2 by 2. Now, if it's 3 by 3, still -1 to 1, -1 to 1. 3 by 3. The Gaussian point will look like this. It is symmetric. So you have 1 point here, 1 point here, 1 point here. That's a 3 by, how it looks like a 3 by 3 Gaussian integration. According to the table, this is 0.577 something, and this is 0.774 something. Okay, so the point is even biased more towards the edge. And this one actually I would draw it a little bit closer. Half, but just a little bit. Yeah, it's like this. Okay, this is up to about that point. So this is the Gaussian point distribution. Now, I think it's important to have to remember the pictures of those Gaussian point distributions, so you know, you have a clear idea when we perform integration, what are the locations of those integration points. Okay. Well, I think that's all for today. We conclude chapter 9. The next lecture will focus on the integration of the boundary of the body force term and the traction force term, which is a little also involves some special treatment. Okay, thanks.